Here is a statement that will probably annoy you. Time does not flow forward. Not really. Not at the level where the universe does its actual work. I know that sounds wrong. I know that right now, in this moment, you feel the weight of the past behind you and the pull of the future ahead of you. You remember breakfast, you are planning dinner. You have a very strong sense that yesterday was real and yesterday is gone. And I am not here to tell you that your experience is a lie, but I am here to tell you that your experience is not the whole story. And the gap between your experience of time and what physics actually says about time is one of the strangest and most productive gaps in the history of science. It is a gap that, when a young physicist in Princeton looked at it honestly and refused to look away, gave him the tools to build one of the most precise theories in the history of human thought. A theory so accurate that if you used it to measure the width of North America, it would be off by less than the width of a single human hair. That gap, that paradox, that refusal to pretend time was simpler than it is, that is what we are going to talk about today. Let me start somewhere you probably did not expect. Let me start with a broken glass. You drop a glass, it falls, it hits the floor, it shatters, pieces scatter in every direction. You look at the mess and you think, well, that is that. Now imagine I film this and I play it back to you. Forward, the glass falls and breaks. Backward, the pieces slide together from the floor, assemble themselves into a perfect glass, and leap back into your hand. One of these films looks completely normal, the other looks completely absurd. You would know immediately which direction is which, and this is the thing that should bother you. Because if you look at the actual equations that govern how those glass molecules move, how they push on each other, how forces act between them, those equations do not care which direction the film runs. They work the same both ways. The laws of motion are what physicists call time symmetric. Run them forward, you get a valid trajectory. Run them backward, you still get a valid trajectory. Nature's rule book, at the level of individual atoms, does not have a stamp on it that says this way only. And yet, you and I live in a world where glasses shatter and do not reassemble. We remember the past, but not the future. We grow older, never younger. There is an arrow in our experience, a definite direction, and that arrow is nowhere to be found in the basic equations. This is the first piece of the puzzle. Hold it. Now let me give you the second piece. And this one is even stranger. You probably learned at some point that light is a wave, and also that light is a particle. And you probably nodded along because you had heard that before and it seemed like one of those things you were just supposed to accept. But let me ask you to not accept it yet. Let me ask you to actually sit with how bizarre it is. Take a source of light, a single tiny source. Fire photons one at a time toward a screen with two small slits in it. One photon, then another, then another. Each photon lands at a specific point on the screen behind it. Tick, 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 now wait. After many photons, a pattern builds up. Stripes of light and dark alternating. An interference pattern, the kind of pattern you get when waves overlap and reinforce or cancel each other. But you fired one photon at a time. Each photon is alone. There is nothing to interfere with. And yet the pattern appears. The only way to explain this is to say that somehow each individual photon went through both slits and interfered with itself. Not in a sloppy metaphorical way. Literally, mathematically, in order to reproduce what is observed, you have to treat each photon as if it explored both paths at once, combined the possibilities, and arrived at the screen according to that combination. This is not a gap in our knowledge. This is not us saying we do not know which slit the photon went through. We have done experiments to check. When you put a detector at the slits to find out which one the photon took, the interference pattern disappears. The photon suddenly picks a single path. The act of finding out which way it went changes how it behaves. Nature is watching you watch it, and when you look, nature stops exploring and starts committing. This is the heart of quantum mechanics, and it is the source of a very deep problem. Because if a single particle genuinely explores multiple paths before you look, and everyday experience gives you one definite past, then somewhere between the quantum and the everyday, Something is collapsing all that richness into one single story. And physicists spent decades arguing about what that something was. Some said it was the act of measurement. Some said it was consciousness. Some built elaborate mathematical machinery to handle it. And most of the machinery worked in the sense that it gave correct answers, but it felt patched together, like someone had taken a beautiful clock and fixed a crack with masking tape. It ran, but you could see the tape. In the late 1940s, a young physicist named Richard Feynman looked at all of this machinery and thought there had to be a better way to understand it. Not just a way that gave the right answer, but a way that showed you why the right answer was the right answer. He was sitting with his doctoral advisor, a man named John Wheeler, who had a habit of proposing ideas so wild that students could not tell if he was being serious or poetic. Wheeler suggested something that most people would have dismissed immediately. What if the electron knows it is going to be measured in the future? What if the future can influence the past? And instead of backing away from this, Feynman leaned in. He started asking a question that turned out to be one of the most generative questions in the history of physics. What if instead of asking which path does the particle take, we ask what happens when we add up all possible paths? Let me show you what that means. Imagine you want to know how a particle gets from point A to point B. In classical physics, there is one path. The path of least action, the smooth, efficient trajectory that Newton's equations would predict. The particle goes there, end of story. But Feynman said, what if the particle does not go there? What if nature considers every conceivable path between A and B, not just the sensible straight line, not just a gentle curve, every path, the path that goes backward first and then forward, the path that takes a detour to the moon and comes back, the path that wiggles like a seismograph during an earthquake, every single one. At first, this sounds like chaos. If the particle can take any path, how do you ever predict anything? The answer is interference. Each path contributes something to the final result. You can think of it as each path carrying a tiny arrow, a little rotating pointer. The arrow has a direction and a length. You add up all the arrows from all the paths. And here is the remarkable thing. For most paths, especially the crazy ones, the neighboring paths point in completely different directions. They cancel each other out. A path that goes to the moon and back is surrounded by paths that are very similar, and those similar paths all point in different directions, and they annihilate each other in the sum. There is one family of paths where this cancellation does not happen. Paths near the classical path, near the smooth, efficient trajectory Newton would have predicted. Near these paths, the neighboring arrows all point in roughly the same direction. They add up, they reinforce, they survive the sum. And what you get out is the classical path. The ordinary sensible trajectory you would have predicted anyway. So here is the extraordinary thing. Classical physics does not have to be imposed from outside. Classical physics falls out naturally as what survives when quantum possibilities interfere with each other. The behavior you see every day is not a separate set of rules for large objects. It is the residue left over when quantum richness filters itself through interference. The familiar world is what remains after the noise cancels out. It is like listening to an orchestra play a chord and hearing one note dominate because all the others happen to cancel. The note that stands out is real. But the rich texture underneath it is also real, and it is what produced the note in the first place. Now, here is where time enters and causes its trouble. When Feynman wrote down this sum over paths, he had to include time. A path is not just a route through space. It is a route through space and time. When he listed all possible paths, he could not logically forbid paths that did strange things with time, paths that paused, paths that looped, and in particular, paths that for a short stretch ran backward in time before turning around and going forward again. If you exclude those paths, you break the mathematics. The interference does not work properly. The predictions go wrong. Experiment tells you that you went wrong, so you cannot exclude them. You have to include them. And this is where the paradox becomes productive rather than paralyzing. Because once you include paths that run backward in time, and you check what they actually contribute to the sum, you find that in almost every situation they contribute exactly nothing. The backward time paths are surrounded by neighbors that point in all different directions. They cancel out almost completely, just like the path to the moon cancels out. They are in the sum, they are allowed to be in the sum, but they do not win. They are outcompeted by the forward paths, which reinforce each other. So the arrow of time that you experience, that deep sense that the past is fixed and the future is open, that is not a fundamental rule engraved in the laws of nature. It is what happens when you let all possibilities compete and see which ones survive. It is an emergent property. It rises from the bottom up rather than being imposed from the top down. And that is a deeply different way of understanding why the world is the way it is. Let me give you an analogy that I think captures the spirit of this. Imagine a crowded marketplace. Hundreds of vendors, hundreds of buyers, all talking at once, haggling, shouting offers, making deals. The noise is tremendous. You cannot follow any single conversation. And yet, out of all that chaos, prices settle. A price for bread emerges. A price for fish emerges. Nobody decided those prices from outside. Nobody imposed them. They arose from the interference of 1 million individual negotiations, each tiny and local, adding up to a stable collective result. The price is the residue of the chaos. Now take away the chaos and try to explain the price. You cannot. The price only makes sense as the outcome of the process that produced it. The classical path through space-time is the price. The quantum possibilities are the marketplace. You cannot understand the outcome without understanding the process that generated it, even though the process involves a kind of exploration that looks nothing like the clean, orderly behavior you observe. Now, let me tell you what happens when you apply this machinery to one of the strangest ideas in physics, the idea of antimatter. When physicists in the early part of the 20th century started working out the equations for electrons at high speeds, equations that combined quantum mechanics with special relativity, they got answers that made no sense. The equations had two solutions, one for electrons, which was fine, and one for a particle with the same mass as the electron, but opposite charge. At first, people tried to throw that second solution away. Maybe it was mathematical noise, maybe it was an artifact of the equations, but it was not. Experiments eventually produced exactly this particle, the positron. A particle identical to the electron in every way except that its charge is positive where the electron's is negative. Antimatter was real. Now, when Feynman applied his path integral picture to this, something beautiful happened. He did not need to add antimatter as a separate ingredient. He did not need a new set of equations or a new set of rules. The positron fell out automatically. It was already there, hiding in the paths that ran backward in time. An electron traveling backward along a segment of its path through space-time looks, to the mathematics, identical to a positron traveling forward. It has the same mass. Its charge appears reversed because a negative charge moving backward in time contributes to the accounting the same way a positive charge moving forward does. This is not a trick. This is not wordplay. The mathematics demands it. And the fact that it works, that this way of looking at the problem reproduces the correct behavior of both matter and antimatter from a single unified accounting scheme, tells you something deep. It tells you that what we call a particle and what we call an antiparticle may not be two fundamentally different things. They may be two perspectives on the same underlying process. One is a path going this way through time, the other is a path going that way, and when you add them all together in the sum, you get the world. Feynman did not stop there. He took this picture and he drew it, literally drew it. He invented a set of diagrams, little pictures that represented the contributions to the sum over paths in a way that a physicist could look at and immediately understand what calculation needed to be done. An electron moving forward through time is a line with an arrow pointing forward. A positron is a line with an arrow pointing backward. A photon, a particle of light, is a squiggly line. When an electron emits a photon, the lines meet at a point. When a photon is absorbed, the lines meet again. And an interaction between two electrons can be drawn as two straight lines, connected by a squiggly line representing the photon they exchanged. What had been a wall of algebra became a picture you could read. And not just read. Each picture corresponded to a precise mathematical expression. You looked at the picture and you knew exactly what to calculate. More complicated interactions gave more complicated pictures, but the pictures could be ranked by how much they contributed to the final answer. The simplest picture gave you a rough estimate. Each layer of complexity gave you a more accurate correction, and the accuracy was extraordinary. The theory made a prediction for a quantity called the magnetic moment of the electron, a measure of how strongly the electron behaves like a tiny magnet. The prediction matched experiment to more than 10 decimal places. No other theory in the history of science has ever matched experiment with that precision. It is as if you predicted the distance from New York to Los Angeles and got it right to within the thickness of an atom. This whole framework, the sum over all paths, the inclusion of time running in any direction, the pictures that made the calculation visible, it was called quantum electrodynamics, QED for short. And it earned Feynman, along with Julian Schwinger and Sine-Ichiro Tomonaga, who arrived at related ideas by different routes, the Nobel Prize in Physics in 1965. Now, let us come back to the paradox, because we have not resolved it, we have not made it comfortable. We have only shown why it is productive to live with it rather than run away from it. The paradox is this. At the level of fundamental physics, time has no preferred direction. The equations are symmetric. Backward in time paths are allowed and must be included. And yet you and I live in a world with a very clear arrow of time. We remember the past, we do not remember the future. Coffee cools down in a cup, it does not spontaneously heat back up. Order decays into disorder. Where does the arrow come from if the equations do not have one? The answer is entropy, and it is a statistical answer, not a mechanical one. Here's what I mean. Think of a box divided down the middle by a removable partition. On the left side, you put a gas. Molecules bouncing around. On the right side, nothing. Vacuum, now remove the partition. The gas expands, it fills the whole box. You wait an hour, a day, a year. The gas does not spontaneously retreat back to the left side and leave the right side empty. That never happens. And yet, if you look at any individual molecule and track its motion, that motion is completely reversible. Every collision is reversible. Every bounce is reversible. There is nothing in the rules for individual molecules that says you cannot go back. What makes the return impossible is not a law, it is probability. There are a stupendous number of ways for molecules to be spread out evenly across the box. There are very few ways for them all to be crammed on the left. When you start in the crammed state and let the molecules bounce around randomly, they drift toward the spread out state simply because there are more spread out states to drift to. If you waited long enough, much longer than the age of the universe, the molecules might spontaneously return to the left side. The physics permits it. The statistics forbid it on any time scale that matters. The arrow of time is an arrow of probability. It points in the direction of increasing disorder. And it is so overwhelmingly strong in practice that it feels like a law, feels like a fundamental rule, feels as absolute as anything you have ever experienced. But it is not carved into the equations. It rises from the enormous number of possibilities available to large systems, and this connects directly to the path integral picture. When Feynman summed over all paths, paths that ran forward in time and backward in time, all contributed. But the paths running forward in time outnumbered and overpowered the backward ones by a factor that makes the probability of a gas reconcentrating itself look like a near certainty by comparison. The forward paths won not because they were obeying a rule, but because there were so many more of them pointing in the same direction. The arrow of time that you feel is the arrow of interference. The paths pointing backward cancel. The paths pointing forward reinforce. And when you are made of an unimaginable number of atoms, all of them running this calculation simultaneously, the reinforcement is so overwhelming that you could never perceive anything else. Let me sit with one more idea, because I think it is the one that changes how you see things permanently. You think of yourself as moving through time. You have a past behind you and a future ahead. You exist at a point called now, and you are carried forward whether you like it or not. This is an entirely reasonable way to experience life. But there is another way to think about it that the physics actually suggests. Instead of thinking of yourself as a thing moving through time, think of yourself as a pattern drawn in time. The same way a melody is not one note that moves through the song, but a collection of notes arranged in a particular order through time. You are not moving through the tape. You are the tape. Your entire history, every moment from birth to death, is a pattern in space-time, a shape drawn in 4 dimensions. And the question of which way time flows becomes a question about the shape of the pattern, not about the motion of something through it. This picture, sometimes called the block universe, is deeply implied by relativity. In relativity, 2 observers moving at different speeds can disagree about which of 2 events happened first. There is no fact of the matter that is the same for all observers about the ordering of events that are separated in space. Time ordering is perspective dependent for events that do not directly influence each other. This does not make your experiences less real. Your memory of breakfast is real. Your anticipation of dinner is real. But the direction of that sequence may not be a feature of the universe. It may be a feature of the particular shape of pattern that you are. A pattern that includes memories pointing in one direction and predictions pointing in the other. The asymmetry is in the structure of your consciousness, not in the fabric of space-time itself. I realize this is uncomfortable. Good. Discomfort is where physics lives. The moments in the history of science where people got comfortable are the moments where progress slowed. The moments where someone said, wait, something does not add up, and actually meant it instead of just nodding along, those are the moments that moved things forward. Feynman had that quality in abundance. He was constitutionally unable to pretend he understood something when he did not. He would work on a problem until he could explain it clearly, and if he could not explain it clearly, he took that as evidence that he did not actually understand it yet. Not that the problem was too hard for explaining, but that his own understanding was incomplete. He said once that if you cannot explain something in simple terms, you do not really understand it. And I think he was right. Not because simple explanations are always available, sometimes they are not, but because the attempt to find a simple explanation is the most honest test of whether your understanding is real or merely formal. The path integral is a simple idea dressed in complicated mathematics. The simple idea is this. Instead of asking what happened, ask what could have happened. Sum over all possibilities. Let interference decide what survives. What survives is what you observe. Everything else cancels. And if you do this honestly, without flinching from paths that seem absurd, without excluding trajectories because they violate your intuitions about time, you get a description of nature that is more accurate than anything that came before it. The strange paths are not a bug in the method. They are the reason the method works. They are the part of the sum that prevents naive classical thinking from being exactly wrong by letting it be approximately right. Every exception, every quantum weirdness, every antimatter particle is a reminder that the strange paths are there, doing their accounting in the background, keeping the universe honest. So where does this leave you? It leaves you with a choice about how to think about time. You can think of time as a river you are riding on, moving forward whether you like it or not, the past fixed and the future open, the arrow permanent and fundamental. That is a useful picture for everyday life. It will serve you well. Or you can think of time as a coordinate in a richer landscape where past and future are both real parts of a 4-dimensional pattern, where the arrow you feel is the result of interference and entropy and probability, where backward in time paths contribute silently to every quantum event that has ever occurred, and where the certainty of your forward motion is not a rule but a residue. Both pictures describe the same world. The second picture, though it is harder to hold in your head, is the one that lets you calculate the magnetic moment of the electron to 10 decimal places. It is the one that unifies matter and antimatter. It is the one that makes the machinery of particles and their interactions visible as drawings rather than walls of algebra. It is the one that earned a Nobel Prize. There is a lesson in that which has nothing to do with physics. The lesson is that fighting with reality because it does not match your intuition is an expensive strategy. Nature is not obliged to make sense to us. It does not know we exist. It does not arrange itself for our convenience. When the equations tell you that backward in time paths must be included, the correct response is not to argue. The correct response is to include them and see what happens. What happened, in this case, was one of the great theories in the history of human thought. Not despite the paradox, because of it. Because someone was brave enough or stubborn enough or curious enough to let the paradox be what it was and follow it to see where it led. The night sky is dark because the universe is young. Electricity flows through the field around the wire, not through the wire itself. Ice floats because hydrogen bonds force a lattice that is lighter than the liquid. And time, at the deepest level of the physics we know, does not flow in one direction. It is summed over. And what you feel as the present moment, that vivid, undeniable sense of now moving forward into then, is the residue of an interference calculation that is running in every atom of your body simultaneously, a calculation so overwhelmingly biased toward forward paths by sheer weight of numbers that you have never had and never will have any reason to notice the backward ones. But they are there. They have always been there. They are part of why you are there. And I think that is worth knowing. I think knowing that changes something. Not about your schedule or your commute or your dinner plans, but about what you understand yourself to be. You are not riding the river of time. You are a pattern in space-time assembled by a universe that evaluated every possibility and settled on you as the outcome. Atoms with curiosity. Matter that turned around and stared at the equations that made it and wondered if they could have gone another way. They could have. They all contributed. Most of them canceled out. But here you are, the result of the sum. If that does not strike you as extraordinary, you have not looked at it closely enough. Look again. Let's keep finding things out.